Pradeep Suri. Author and researcher. Design, AI predictive model for, just-in-time delivery and design of deep neural networks. 1.0 Problem definition. For example, it could be predicting demand, optimizing delivery routes, or managing inventory. 2.0 Data collection. Gather relevant data for our problem. This could include historical order data, customer information, delivery route data, weather information, and more. Ensure data quality and cleanliness. Clean data set, clean, pre-process, and transform the data as needed. This may involve handling missing values, encoding categorical variables, and normalizing numerical features. Split data into training, validation, and test sets. Train deep neural network on the training data and monitor its performance on the validation set. Use appropriate loss functions and optimization techniques. 3.0 Feature engineering. Create relevant features that can enhance the predictive power of our model. For example, we might create time-based features, customer segmentation features, or geographical features. 4.0 Model selection. Choose appropriate deep learning architectures for our problem. Common choices include recurrent neural networks, RNNs, long short-term memory networks, LSTMs, or transformer models. Model design. Design the architecture of deep neural networks. Consider factors like the number of layers, the number of neurons in each layer, and the activation functions. 5.0 Hyperparameter tuning. Fine-tune hyperparameters such as learning rate, batch size, and dropout rate to improve model performance. Use techniques like grid search or Bayesian optimization. 6.0 Regularization. Implement regularization techniques like dropout, L1, or L2 regularization to prevent overfitting, especially if the dataset is small. 7.0 Evaluation. Evaluate the model's performance using relevant metrics such as mean absolute error, MA, mean squared error, MSE, or root mean squared error, RMSE. Adjust the designed model and training process based on the evaluation results. 8.0 Deployment. Once our model performs satisfactorily, deploy it in a production environment. This may involve setting up APIs or integrating them with our just-in-time delivery system. 9.0 Real-time predictions. Configure the AI model to make real-time predictions by integrating it with our delivery system. Ensure that it can handle incoming data streams and make predictions promptly. 10.0 Monitoring and maintenance. Continuously monitor the model's performance in production. Retrain the model periodically with new data to ensure it remains accurate over time. Implement mechanisms to handle concept drift if the data distribution changes. 11.0 Feedback loop. Establish a feedback loop where real-world delivery outcomes are used to improve and retrain the model. This helps in continuous model improvement. Scaling. As our just-in-time delivery system grows, consider scaling our AI infrastructure to handle increased demand and data volumes. 12.0 Ethical considerations. We have to consider ethical implications, such as fairness, bias, and privacy, in our AI models and data handling practices. Remember that the success of our just-in-time delivery AI model depends on the quality of data, continuous refinement, and its integration into our operational processes. It is also essential to stay up to date with the latest advancements in AI and deep learning to ensure our model remains competitive and effective. Solution assumption. Clean input data set. Historical order data. Customer information, preferences, location, order history. Delivery route data, maps, traffic information. Weather information. Inventory data, stock levels, supplier information. Requirement calculation based on vendor lead time. Output from neural network. Purchase order. Funds required for vendor patent. Hidden layer. 3 hidden layers. Hidden layer calculation. Calculating the number of neurons, units, in the hidden layers of a neural network is an important step in designing our deep learning model. The number of hidden neurons can significantly affect our model's performance. While there's no one-size-fits-all answer, you can follow some general guidelines and practices to determine an appropriate number of neurons for our specific problem. 1. Start conservatively. It's often a good practice to start with a relatively small number of neurons in our hidden layers and then increase the complexity as needed. This helps prevent overfitting and keeps our model efficient. 2. Consider model complexity. The complexity of our problem and the complexity of our data should guide our decision. More complex problems may require larger hidden layers. 3. Rule of thumb. A commonly used rule of thumb is to have a number of neurons in each hidden layer somewhere between the number of neurons in the input layer and the number of neurons in the output layer. You can calculate this as follows. Number of neurons in the input layer. This depends on the number of features in our input data. For example, if you have 10 input features, our input layer will have 10 neurons. Number of neurons in the output layer. This depends on the number of output units you need. In our case, you have 2 output units, purchase order and funds required, so our output layer will have 2 neurons. A common practice is to take the average of the neurons in the input and output layers as a starting point. In this case, it would be 10 plus 2, / 2 equals 6 neurons per hidden layer. For experiment and fine-tune, neural network design is often an iterative process. You can start with a conservative number of neurons, train our model, and then evaluate its performance. If the model underfits, performs poorly, you can increase the number of neurons in the hidden layers. If it overfits, performs well on training data but poorly on validation / test data, you might need to reduce the number of neurons or apply regularization techniques. 5. Consider computational resources. Keep in mind the computational resources available to you. Very deep or wide networks with many neurons can be computationally expensive to train. 6. Use cross-validation. Cross-validation can help you estimate how well our model generalizes to unseen data. Experiment with different hidden layer sizes and observe how our model performs on validation data during cross-validation. 7. Domain knowledge. If you have domain-specific knowledge about our problem, it can guide our choice of hidden layer size. For example, if you know that certain patterns or interactions in the data require a specific level of complexity, you can adjust our hidden layer accordingly. Remember that there's no one-size-fits-all answer, and the ideal number of neurons in our hidden layers may require experimentation and fine-tuning. It's essential to strike a balance between model complexity and generalization to achieve the best performance for our specific just-in-time delivery prediction problem. In our exercise book, please write a Python program. Thank you.